Hello everybody, welcome to our video solution to problem 7 from Superquiz 3. In this problem, we're given an iterated double integral, and we would like to evaluate it by converting it into polar coordinates. So first thing we'd like to do is maybe try to sketch the region that we know is the domain of integration here. So we note first we're integrating y from -3 to 0, and x, well, it actually depends on the y. It goes from -√9 minus y squared to 0. And as soon as we see this, we should be thinking circle. In fact, that 9 there tells us we should be thinking a circle of radius 3. So let's try to draw what we have there. Now it says the y is going from -3 to 0. So -3, maybe that could be down here, 0 is here. So we're just living down below the axis. So this region actually doesn't have any part of the upper half plane. Now, this x equals -√9 minus y squared. Again, this is telling us we should have a circle of radius 3. And the x coordinate can't be any bigger than 0. So actually, not only are we going to be in the lower half plane, but we also have to be over here to the left of the y-axis, right? The x value can't go past 0. So we're over here in quadrant 3. So what we must be getting then is just, well, let's see if we can draw that a little better, just this part of the circle. All right, so this would keep going. Right, if we want to draw a circle of radius 3, but we only want the part that is in this third quadrant because we need the y, right, to be between -3 and 0, and we need the x to be between the circle, okay, and the y-axis. It has to go, the x-coordinate can't go past 0. So our domain of integration is going to be this sector of the circle. All right, well, can we write that down in polar coordinates? So in polar coordinates, we have an r and a theta, and the r is the distance that any point in here is away from the origin. Well, if I take some point, connect it with a little line, I can ask how long is that line? And since this is a circle of radius 3, the radius, or the distance to this origin, can't be any bigger than 3. And of course, it can't be any smaller than 0. And you can see we're actually getting every value in between. So r will go between 0 and 3. How about the theta? Well, normally the theta for a circle would be 0 to 2 pi. You have to go all the way around. But we don't get this first quadrant. So 0 to pi over 2, that's not going to be in there. And pi over 2 to pi, that's not going to be in there. But pi to 3 pi over 2, yeah, that's the answer right there. So our theta will go between pi and 3 pi over 2. Okay, so remember theta is the angle, right, if you draw this ray out to a point, that's the angle you get with the positive x-axis. So we get to start from the 0 line, go all the way around here. That'll give us some angle between pi and 3 pi over 2. All right, well now let's try converting our double integral. So, well, I'll just give a name to this so I don't have to copy the whole thing. We'll call it I. So I is going to equal the integral from, well, let's see, r goes from 0 to 3. Theta goes from 0, not 0, what do we say, pi to 3 pi over 2. All right, now we have this xy, and that's not written in terms of r's and thetas. So we need to use our conversion rules. So x converts into r cosine theta, and y converts into r sine of theta. So x times y will convert into r squared cosine of theta sine of theta. Okay, now we have dx dy, and in a generic double integral, right, that would be our dA. But when we convert to polar coordinates, our dA is no longer going to be in terms of x's and y's. It will be in r's and thetas. And when we convert to r's and thetas, right, we get a dr, we get a d theta, right, in some order. I'll put the theta first. But there's also what I call the cost of doing business, or what the mathematicians call the Jacobian. It's this extra factor, right, of an r here. So we're actually going to get an r d theta dr. All right, so that is how we can convert this rectangular double iterated integral into a polar double iterated integral. Now, if we want to solve this, well, we'll note we're first integrating with respect to theta, and these r's have nothing to do with that, so we can pull those out. In fact, we can basically split these integrals apart because there's no interplay between the r's and the thetas here. So r goes from 0 to 3, and then we have an r squared and an r, that's r cubed times dr. And then we have an integral theta goes from pi to 3 pi over 2. And we have cosine of theta times sine of theta, d theta. All right, the first integral, very, very routine. You anti-differentiate, get r to the 4th over 4, evaluate between 0 and 3. Which, heck, we might as well just go to the next line here. We know there's more coming, but let's see. At 0, of course, nothing's going to happen. At 3, you're going to get 3 to the 4th, which is 81 over 4. Cool, so we got that taken care of. How about this one? Well, there's a couple ways you might approach this. You could do a substitution. So, for example, if you did u equals sine of theta, so say we do u equals sine of theta, then du is going to be cosine of theta d theta. All right, so that's pretty nice. Now you're just basically integrating u. It'll be u squared over 2, which means sine squared over 2. Alternatively, you could use the identity that cosine of theta, sine of theta, is 1/2 sine of 2 theta. Right? And so then you'll end up integrating sine of 2 theta, which is actually pretty easy to do. Okay. Either way, we're going to end up over here, well, with something. I'm going to use the first method. Why not? So we end up with sine squared over 2 evaluated between pi and 3 pi over 2. So let's see. At 3 pi over 2, ooh, what's the sine at 3 pi over 2? Well, 3 pi over 2 is down here. The sine is the height, so that's going to be -1. But then you're going to square it, and you get +1, and then you get to cut it in half. All right, now what happens when we go to pi? Well, sine of pi, that's the height at pi. Well, sine is 0 there, so you just get a -0. And so in total, we'll have 81/4 times 1/2, which is 81 over 8.